Okay, dear students, welcome to physics class of YouTube. In the previous session, previous video class, we have discussed the Faraday's law of electromagnetic induction, that is how to determine the value of the induced EMF or the induced current, how we can calculate, and the Lenz's law. The Lenz's law, which gives the polarity of the induced current or the induced EMF, and it supports the law of conservation of energy. The significance of the Lenz's law is law of conservation of energy. The next point we have to discuss here is the methods of changing the magnetic flux linking with the coil. How many methods or how many ways we can change the magnetic flux linked with the coil, right? So let us discuss here the methods, and then we have to derive the expression for the motional EMF, right? Motional EMF, what is motional EMF, and hence we have to derive the expression here. Now the first method here, the changing the strength of the magnetic field. We can change the magnetic flux linked with the coil. So strength of the magnetic field and change ಮಾಡ್ಕೊಂಡು ಕೂಡ ನಾವು ಏನು ಮಾಡಬಹುದಿಲ್ಲ, we can change the magnetic flux linking with the coil. Strength of magnetic field increase ಅಥವಾ decrease ಮಾಡೋದ್ರ ಮುಖಾಂತರ ನಾವು ಏನು ಮಾಡಬಹುದ್ರಿ, magnetic flux linked with the coil which can be changed. First one is we can change the magnetic field B, and second one by changing the area of the coil. Area of the coil ಅನ್ನು change ಮಾಡೋದ್ರ ಮುಖಾಂತರ ಏನು ಮಾಡಬಹುದ್ರಿ, we can change here what, the magnetic flux linked with the coil. So you know that the magnetic flux is given by the formula pi b is equal to BA cos theta. So the first one is here B, right? By changing the strength of the magnetic field B, we can change the magnetic flux linked with the coil. And second one, by changing the area of the coil, the A value, area of the coil, if you change, again the magnetic flux linked with the coil, that also can be changed here. And third one, by changing the orientation of the coil with respect to the magnetic field. That means what, we have to change the value of theta. Theta value ಅನ್ನು change ಮಾಡೋದ್ರ ಮುಖಾಂತರ ಏನು ಮಾಡಬಹುದ್ರಿ, we can change here what, the magnetic flux linking with the coil. Orientation, coil orientation change ಮಾಡಬಹುದ್ರಿ with respect to the magnetic field direction, right? So that means what, here theta is the angle between the direction of the magnetic field and the area vector, that is the area vector which is normal to the plane, right? That means what, area vector which is normal to the area. Now in vector draw ಮಾಡಿರ್ತೇವೆ perpendicular or normal to the area. So other the angle, right? For example, this is a coil here, we have a coil here, right? We have a coil here, right? So normal drawn to this is A, right? And this is equal to what, is the direction of magnetic field. This is area vector. So ಇದನ್ನ ಏನು ಮಾಡ್ತೀವಿ ನಾವು, that magnetic flux passing through the given area is equal to what, the number of magnetic field lines passing through the given area is equal to magnetic flux. So pi b is equal to BA cos theta ಅಂತ ಹೇಳ್ತೀವಿ. So this is what the angle theta will define. So when this angle is 90 degree, the flux is minimum, and when this theta is equal to 0 degree, the flux passing through the given area is maximum. So these cases already we have discussed, right? So what are the points, the methods of changing the magnetic flux linking with the coil here is what, by changing the strength of the magnetic field, by changing the area of the coil, and by changing the area, by changing the orientation of the coil with respect to the magnetic field. So theta, A, and by changing these values we can change the magnetic flux linked with the coil. Now consider here, by considering one of the method here, right, that is by changing the area of the coil, how we can produce the EMF. Let us discuss here, that is called as the motional EMF, right? Now let us discuss what is the motional EMF, and hence we have to derive the expression for the motional EMF here. Now let us understand here what is meant by motional EMF, and hence we have to derive the expression for the motional EMF here. So as now we have discussed here the methods of changing the magnetic flux linked with the coil. By changing the area of the coil, by changing the strength of the magnetic field, and by changing the orientation of the coil with the magnetic field, we can change the magnetic flux linked with the coil. So in this point, what we are doing here, by changing the area of the loop or by changing the area of the rectangular conductor here, we are changing the magnetic flux linked with the coil, and hence we have to induce the EMF here, right? By changing the area, we are inducing the EMF, and hence we have to calculate the expression for the motional EMF. So what is meant by motional EMF? The EMF induced across the ends of the conductor when it moves in a magnetic field, right? The EMF induced, across the ends of the conductor when it moves in a magnetic field. When it moves in a magnetic field. When it moves in a magnetic field is called motional EMF. Is called motional EMF. So this is a very important 3-mark question in electromagnetic induction. What is motional EMF, and hence derive the expression of the here 3 marks here. So what is motional EMF here? The EMF induced across the ends of the conductor when it moves in a magnetic field is called as the motional EMF in the conductor, right? So ಇಲ್ಲಿ ಏನು ಮಾಡ್ತೀವಿ ನಾವು ಕಂಡಕ್ಟರ್ ಅನ್ನು ಮೂವ್ ಮಾಡಿ ಏರಿಯಾ ಆಫ್ ದ ಕಾಯಿಲ್ ಚೇಂಜ್ ಮಾಡ್ತೀವಿ. ಏರಿಯಾ ಆಫ್ ದ ಕಾಯಿಲ್ ಚೇಂಜ್ ಮಾಡಿದ ನಂತರ ಏನಾಗ್ತದೆ ಇಲ್ಲಿ magnetic flux linked with the coil changes. So magnetic flux change ಆಗೋದ್ರಿಂದ EMF induce ಆಗುತ್ತೆ. So in this way we have to calculate here the motional EMF. So note down this definition. The EMF induced across the ends of the conductor, when it moves in a magnetic field, right? So when it moves in a magnetic field, so magnetic field ಒಳಗ ಕಂಡಕ್ಟರ್ ಅನ್ನು ಮೂವ್ ಮಾಡಿ ನಾವು EMF induce ಮಾಡ್ತೀವಿ. So this is called as what? The motional EMF. So movement ಮಾಡೋದ್ರಿಂದ motional EMF ಅಂತ ಕರೀತೀವಿ, right? Now let us derive the expression for the motional EMF. So from the figure we have to derive it. So expression for the motional EMF here. So let us consider here SMNR. So SMNR is a metallic frame here. Let SMNR is what here? It is a metallic frame. So ನಮ್ಮ ಹತ್ರ ಏನಾಗಿದೆ here we have what here? SMNR is a metallic frame, right? SMNR is a metallic frame and it is placed in a uniform magnetic field. So in metallic frame ಅಂದರೆ SMNR ಇದನ್ನ ನಾವು ಯೂನಿಫಾರ್ಮ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಒಳಗೆ ಇಟ್ಟಿದ್ದೀವಿ, right? So this magnetic field is perpendicular to the plane. So cross symbols ತೋರಿಸಿದ್ದು ಏನು ಇಂಡಿಕೇಟ್ ಮಾಡ್ತಿದ್ರಿ? The magnetic field is perpendicular to the plane, right? So SMNR is a metallic frame which is placed in a uniform magnetic field, and the magnetic field is perpendicular to the plane. Now, so one more metallic rod PQ. PQ is a metallic rod which is placed on the what? Metallic frame SMNR. The metallic rod PQ which is placed on the metallic frame SMNR ಮೇಲೆ ಇದನ್ನ ಪ್ಲೇಸ್ ಮಾಡಿದ್ದೀವಿ. Because of what? Which can be moved towards left with a constant velocity v. ಇದನ್ನ ನಾವು ಇದರ ಮೇಲೆ ಇಟ್ಟಿದ್ದೇವೆ, ಇದನ್ನ ಲೆಫ್ಟ್ ಸೈಡ್ ಮೂವ್ ಮಾಡ್ತೇವೆ with a constant velocity v as shown in the figure here. PQ is a metallic rod which is moved to the left with velocity v as shown in the figure here. Now the distance of the rod from the one end of the metallic frame, that is from SR, the distance of the rod PQ from SR, right, that is equal to what? let we can write that RQ is equal to what we can write here, or QR is equal to X. That is the distance of the rod from the one end of the metallic frame, or from the SR. The distance of the rod PQ from SR is equal to what? X. And again the length of the rod is equal to what? L here. PQ is equal to, or SR is equal to L. Right? SR is equal to L. That is the length of the rod. That is equal to PQ is equal to, or SR is equal to L. Right? Now the area of the rectangular conductor. So area that is the area of the rectangular conductor, which becomes what here now? This area. This area is equal to what here? The area of the rectangular conductor now. The area of the rectangular conductor. The area of the rectangular conductor is now becomes what here? So rectangular length into breadth over 3. So x into L. That is equal to what here? Area. Therefore the area of the rectangular conductor A is equal to what? X into L, or L into X. So this is one of the point we have derived here. So now what? Now we have got here the area of the rectangular conductor. Right? So again the magnetic flux enclosed by this PQRS. So E area that is the area of the rectangular loop that is the conductor. Conductor area the magnetic flux again from the definition of magnetic flux. The magnetic flux enclosed by the loop PQRS. The magnetic flux enclosed by the loop PQRS. So E area PQRS area magnetic flux calculate ಮಾಡಬೇಕು. So that is equal to what? Pi is equal to BA cos theta. Right? So theta is equal to ಎಷ್ಟು ಆಗ್ತದೆ ನೋಡಿ ಇಲ್ಲಿ 0 degree. Right? So magnetic field ಈ direction ಒಳಗಡೆ. Right? Magnetic field ಈ direction ಒಳಗಡೆ. Right? Perpendicular to the plane. Again the normal drawn to this area. ಈ area ಗೆ ನಾವು normal draw ಮಾಡಿದ್ರೆ ಅದು ಈ direction ಒಳಗೆ ಬರ್ತದೆ. Right? So then angle between A and B is equal to 0 degree. Right? So pi is equal to BA cos 0 degree. Cos 0 degree. Therefore it becomes what? Cos 0 is 1. So it is equal to BA. Right? B into A is what here? The magnetic flux enclosed by the loop PQRS, but A is equal to what? X into L. So what we can write here then? Pi is equal to what we can write here? B L into X. B L into X. So this is what the magnetic flux linked with the, or the enclosed by the loop PQRS. E loop is magnetic flux B L into X. So now call this as equation 1. So now when we have got the magnetic flux enclosed by the loop or linked with the coil, we can calculate the EMF induced. Right? ಇಲ್ಲಿ rod move ಮಾಡೋದ್ರಿಂದ ಏನಾಗುತ್ತೆ? Magnetic flux linked with the coil changes. The current EMF is induced in the conductor here, and hence current is also induced. Right? So now we have to calculate here the EMF induced in the conductor. So as we move this conductor towards the left side, the magnetic flux linked with the coil changes, right? And hence EMF is induced in it here. ಈ ಕಂಡಕ್ಟರ್ ಏನಂದ್ರೆ ರಾಡ್ ಏನಂದ್ರೆ PQ ಇದನ್ನ ನಾವಿಲ್ಲಿ ಮೆಟಾಲಿಕ್ ಫ್ರೇಮ್ ಮೇಲೆ ಇಟ್ಟಿದ್ದೀವಿ. ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಅಪ್ಲೈ ಮಾಡಿದ್ದೀವಿ. ಇದನ್ನ ಮೂವ್ ಮಾಡ್ತೀನಿ ನಾನು, right? This conductor is moved towards the left with velocity v. The area change ಆಗ್ತಿದೆ. Area of the loop changes, and hence magnetic flux linked with the coil changes, so that EMF is induced in it, right? So that induced EMF, how we can calculate the induced EMF here? The induced EMF I can calculate it by the Faraday's law of electromagnetic induction. Therefore, according to Faraday's law, the induced EMF is equal to, therefore, according to Faraday's law, according to Faraday's law, the induced EMF, that can be calculated here. So what is the Faraday's law? The induced EMF is equal to what? The rate of change of magnetic flux linked with the coil and thread link. You consider right? Therefore, E is equal to what here? The induced EMF is equal to minus d pi by dt. This is from the definition of, or from the law of the Faraday's law of electromagnetic induction, which is used to calculate the EMF. Therefore, E is equal to what? Minus pi is equal to what here? BLX. Therefore, d by dt of BLX. So B and L, we can take it outside the term here. It is E is equal to minus B into L. Right? We are changing the x here. Therefore, it is equal to dx by dt. So, what is the dx by dt here? Right? What is the dx by dt? The rate of change of magnetic distance here. That is equal to what here? Dx by dt is equal to, the dx by dt is equal to what we can write here? That is the velocity, right? So the rate of change of distance with time, we can write it as what? The velocity. So hence what we can write here, the final expression. So therefore this minus dx by dt, which represents what here? The velocity. That is the rod with which the velocity of the rod with which it is moving. Therefore, E is equal to BL into V. So E is equal to, that is the induced EMF. The expression for the induced EMF is equal to what? BL into V. Right? Where V is equal to what? Where V is equal to minus dx by dt. Where V is equal to what? Minus dx by dt. What it represents? Which represents the velocity of the conductor with which it is moving. Now, ಈ ಕಂಡಕ್ಟರ್ ನ ಯಾವ ವೆಲಾಸಿಟಿ ಇಂದ ಮೂವ್ ಮಾಡ್ತಾ ಇದೀವಿ ಅದರ ಮೇಲೆ ಅದು ಏನನ್ನ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ತಿದ್ದೀವಿ. That is what? Minus dx by dt. Minus dx by dt, which indicates the velocity of the conductor pq. Therefore, this expression represents, this is the expression for the induced EMF. Expression for, so E is equal to BLV, which represents the expression for induced EMF. So what is the motional EMF? The EMF induced across the ends of a conductor when it moves in a magnetic field. A EMF induce agide adanna ನಾವು ಯಾವ ರೀತಿ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ತೀವಿ? That is E is equal to BLV. This is the expression for what? The induced EMF. And this expression is called as, and the induced EMF is called as the motional EMF, because of what? By moving the conductor, we are obtaining what here? The induced EMF. The direction of the induced EMF that can be determined here by Fleming's right hand thumb rule. Right? By using the Fleming's right hand thumb rule, it is also called as the generator rule. We can find the direction of the induced current, right? Or the induced EMF. So now let us see here how the Fleming's right hand thumb rule is used to find the direction of the induced current of the induced EMF here. So first three fingers of the right hand are stretched at right angles to each other. That means what here? All the right hand first three fingers, that is thumb, forefinger and central finger or the middle finger. So all these three fingers are stretched at right angles to each other, perpendicular to each other. Then the thumb points in the direction of the motion of the conductor. Thumb points in the direction of the motion of the conductor, and the forefinger, which gives the direction of the magnetic field, and the induced current is determined by the middle finger. Middle finger ಯಾವ direction ಅಲ್ಲಿ ಬರ್ತದೆ ಆ direction ಅಲ್ಲಿ current induce ಆಗಿದೆ ಅಂತ ನಾವಿಲ್ಲಿ ಫೈಂಡ್ ಮಾಡ್ತೀವಿ by using the Fleming's right hand thumb rule, or it is also called as the generator rule. So see here, the motion of the conductor. Now conductor na ಯಾವ direction ಅಲ್ಲಿ move ಮಾಡ್ತಾ ಇದೀವಿ? Magnetic field ಈ direction ಅಲ್ಲಿ ಇದೆ, right? So this is the direction of the magnetic field, and thumb points in the motion of the conductor. Conductor ಈ direction ಅಲ್ಲಿ movement ಆಗ್ತಾ ಇದೆ, and the induced current is determined by the middle finger. That means what? In ಯಾವ direction ಹೋಗುತ್ತೆ ನೋಡ್ರಿ? This is the direction of the forefinger use the direction of the magnetic field. Magnetic field ಈ direction ಅಲ್ಲಿ apply ಮಾಡಿರ್ತೀವಿ, right? Conductor ನ ಈ direction ಅಲ್ಲಿ move ಮಾಡ್ತೀವಿ. ಹಾಗಾದ್ರೆ current ಯಾವ direction ಅಲ್ಲಿ induce ಆಗ್ತೈತ್ರಿ? Middle finger ಯಾವ direction ಅಲ್ಲಿ ಬರ್ತೈತೆ ಅದು. ನಾವು ಯಾವಾಗ ಮೂರು finger ನ right angle stretch ಮಾಡಿರ್ತೀವಿ, right? So this is the direction of the magnetic field, this is the motion of the conductor, and this is the direction of the what? The induced current. So the direction of the induced current will be in this direction, right? The direction of the direction of the current will comes in downward direction in this case, right? So it depends upon what? The motion of the conductor and the magnetic field direction, and we have to find the direction of the induced current. That means what it states? The first three fingers of the right hand are held at right angles to each other, right? Thumb points in the motion of the conductor, forefinger points in the direction of the magnetic field, right? And the middle finger gives the direction of the current train, the direction of the current. So the direction of magnetic field apply ಮಾಡಿದೀವಿ, ಈ direction conductor na move ಮಾಡ್ತಾ ಇದೀವಿ. So in downward direction, that is, you will get the direction of the induced current. So in this way you have to find the direction of the induced EMF by using the Fleming's right hand thumb rule, and it is also called as the generator rule. Okay, in the next video class we will discuss the next point related to what? The electromagnetic induction. Okay, thank you students.